a map from integer lattice into projective space. So we know what the straight line is, and we just assume that the image of an arbitrary point of the integer lattice and its positive direction neighbors is collinear. So the points phi and its nearest neighbors. So this is the shift in the first direction, in the second, in the third direction. Then these points are collinear. And this collinearity restriction imposes a condition for the map, and it in generic we will go to this map in a minute. Let us consider some simpler cases where the map is in the affine coordinates. The collinearity of points phi, phi1 and phi2 written in the non-homogeneous coordinates, just like this is the proportionality of vectors which just show the differences between the points of the affine space. So we have such three linear equations which reflect the collinearity of points, but we can consider the transformation.
Possible. So
yes.
By this transition zip. And then this transition matrix, we'd like to view it as a matrix over the integers.
Just, sorry, I can hear some another talk, so probably.
I think it was.
Okay.
It was question. It was question.
Okay. So let me recall that this gives a transformation between fields x1, x2, and x3. Yes, to new fields. This was just the restricted version of that more generic map. I will show you. Oh, sorry, this was this. So phi are some represent wave function, and this coefficients aij need to satisfy some equations. But when we inserted some restriction between x aij, which will be more transparent later, then this map gives you a map between coefficients x to x tilde, which satisfies the Zamolodchikov property. And maybe let me show this Zamolodchikov property combinatorially. So, can you hear me?
Yeah, we can hear you.
Okay, so the map is in the hexahedron with 1, 2, 3 variables. Yes, but starting from 4-dimensional hexahedron, we can consider various. And what is important are the correct faces. So from 1 to 3, we go to 1 to 3. Just a kind of flip in the hexahedron. Yes, and we, in two ways, which should result from the left and from the right in the same result. And I would like to explain you this picture more geometrically. And it turns out that the map we had here can be splitted into two simpler parts. Into map V, P is just the permutation of the corresponding variables, and the map N satisfies, is given by this form, and it turns out that it satisfies the pentagonal condition, and the map V is given below, and it satisfies the reversed pentagon condition. And
is this an observation, or there is a relation between the tetrahedron maps and pentagon maps? So can you write every tetrahedron map as a decomposition of permutations and pentagon maps?
Certainly, I mean, I don't, not in such a simple case, not in such a simple form, yes, where we have only two such maps. I cannot make such a general statement, but I have some geometric ideas that even some more complicated tetrahedron maps can be decomposed into more complicated sequence of such pentagonal maps. But I cannot formulate at the moment any such statement.
The reason why I'm asking is because last time I asked you if there is lax representations for pentagon maps. So if there is an algorithmic way of how to decompose a tetrahedron map into pentagon maps, maybe not simple as here, maybe you can do the same with the lax representation. They can be decomposed, I don't know, to some kind of
so you said that there is an algorithmic way to...
if there is an algorithmic way, then maybe this will indicate you of what the lax representation of a pentagon map should be.
I think that it may be a good indication that also the lax representation can be found in this way. But let us concentrate on geometric meaning of this map N and V. Yes, the map N is just a relation between coordinates of 4 collinear points. So this is the transformation. Yes. And the map V is also a relation between coordinate or complicated configuration. It is not very complicated, but we have 5 initial points, yes, and we calculate from that coordinate transformation, yes, and these maps satisfy the pentagonal and reversed pentagonal condition. And so an additional slide that if you calculate the inverse of the normalization map N, then, and if you compare with the Veblen map, then you can see that the inverse of N is just the Veblen map, but written in opposite order of multiplication. Similarly, the map V, if you calculate its inverse, is almost the same like the normalization map, but you should multiply in opposite way. Okay, but now let me proceed to something more general. The geometry will be just, I would like to recall that the pairing condition between, between the maps V and N also has geometric meaning. And this consistency between these two Veblen maps gives you the corresponding, the proof that the map which we had here, the map R, satisfies the tetrahedron condition. And now I would like to keep the geometry, but slightly change the algebra. Okay. So let us consider also the 4 collinear points, A, B, C, D. But now the wave function phi has geometric interpretation that the function is given up to a gauge. So if you multiply the homogeneous coordinates by a scalar, you still have the same point of the projective space. And we have the homogeneous coordinates of the 4 points. And in these homogeneous coordinates, the collinearity between A, B, and C points is just the linear relation. So this is the first equation. And we have such a bunch of linear relations between the homogeneous coordinates. And this gives you a transformation between xy and x prime y prime. And you can calculate that this map satisfies the Pentagonal relation. And now this map is for non-commuting symbols. You know how to multiply them. Yes. But the nice observation is that if the x's and y's commute, then this map preserves the following Poisson brackets. So this is the first observation. And this Poisson brackets are quasi-classical limit of the Weil commutation relations. So, and in fact, something similar holds.
Could you please explain in what sense quasi-classical limit? What actually limit you compute?
So you okay, so it if we speak about limit, so it's better to start with non-commutative case and limit. So let me first state the quantum case, and then I will take the limit. So assume that the normalization map preserves the ultra-locality conditions, but the x and y with the same index Q commute. It is this, the Q commutation condition is written here. Yes. Then first the map, the normalization map, preserves the ultra-locality and the commutation relation. Yes. In fact, you can, under some generality conditions, you can reverse the implication in the sense that if you would like the ultra-locality condition initially and the ultra-locality condition preserved by the map, then you need Q commutation conditions. And what is the classical limit? You assume that Q is 1 plus epsilon. And you define your Poisson brackets as like in the relation between standard commutation and Heisenberg relation. So you define your Poisson brackets as the difference between the usual commutation, but divided by that small parameter epsilon. So I do not have a tablet to write down precisely, but you expand Q as 1 plus epsilon, and define your Poisson bracket divided by the epsilon. And what remains is just that product xy, xi, yi. So if you take the logarithm of this commutation relations, you obtain the standard Heisenberg the standard canonical commutation relations. So,
is there any problem with the logarithm? Because a logarithm is for non-commutative variables defined like a series. Now we start series not from 1 but from x and y, you know. Is it any problem there?
So I mean, the transition to the standard canonical commutation relations is, I do not remember precise formulas, but you should have that x and y are exponentials of q and p. I mean, in the standard notation.
That's clear. That's clear.
And okay, so can I go further or? Okay. So then we have the commutation or Q commutation relations from ultra-locality. And now let us go to the next map, to the V map. Also, here we have initial two lines intersecting in point AC. So there are two linear relations. And now we intersect the dashed lines, and dashed lines become solid lines. And this gives you point BD. And we have new linear relations, which essentially allow you to construct the point BD, but you remember that the homogeneous coordinates of phi BD are given up to scalar factor. So in this more complicated map, V, the Veblen map, the coefficient y1 bar is in fact free. Yes, we have freedom of one coefficient. So therefore we can take it as y1. It is lambda. I mean, let us call it lambda. And then the rest of x's and y2 is fixed just by calculations. And you can check that these maps, parametric maps, satisfy the pentagonal condition when the parameters of these 5 maps are related, like B equal H and G is equal CB.
Adam, I'm sorry, I have some subconscious question. Just briefly, is there some dual interpretation of your relation on the top of the list? For point on a line in dual language is the point of the Grassmannian of the 2-dimensional subspace in a 4-dimensional space. Is it relevant to this geometry or not?
I mean, the projective space in general can be considered in the language of Grassmannians, just as the
transpose of the matrix from 4 point on a line, you can obtain 2 space in a 4-dimensional space.
I do not consider this in such a way, because for the 4 points on the line, we didn't have, you mean, can be this picture generalized more?
Okay, we can discuss it later. Thank you.
Okay. I think I've got your point, but okay, we can discuss it later. So now we have this map, lambda. And now we can ask a similar question. Yes. So suppose you would like your map the same Poisson structure. Yes. What type of lambda of the gauge you can take? No. So in order that the Poisson structure would be preserved. So if you are on this classical level, you just insert the map into the Poisson conditions, Poisson structure conditions, and you can find a differential equation for the gauge function lambda. Yes. And above, we have a particular solution for that equation, differential equation. Yes, where alpha and beta are 3 parameters. And if you take such form of the gauge, then you also have the pentagonal condition satisfied, provided now your pairs of parameters for each gauge parameter, so for G, H, A, B, C, so we had before such a relation. Yes. And it, when rewritten in terms of this gauge functions, give you the following relation between the gauge parameters. of these functions. Yes. And similarly, you can do in the non-commutative case, in the sense that you need so you can check, okay, you can check that for the same gauge lambda, but with alpha and beta being the commutative parameters, the Veblen map preserves the ultra-local Weyl commutation relations. Yes. This is just a calculation. And in fact, this is a particular case of something more general. So you can assume the gauge parameter lambda as an arbitrary series with such a single variable. And it also satisfies the Weyl commutation relations. But I don't know then what about the Pentagonal relation? Because then the situation will be much more complicated for coefficients of the series.
But a pentagonal relation, if you take your gauge lambda equal alpha y1 plus beta x1 y2, in non-commutative case will be
also preserved,
also preserved, yeah.
Provided the relation between the coefficients alpha and beta.
So Q will not enter in the pentagonal relation.
Q will not enter into the pentagonal relation.
Okay, thank you.
Okay. And now I would like you to present the corresponding tetrahedron map in the full generality. Yes. So now we have map N, we have map V, and we have the decomposition of the tetrahedron map of the map into two pentagonal maps, N and V. And geometry of the matching condition between Veblen and tetrahedral map remains the same. It was here. I mean, you start from these 7 black points and you go around that star configuration in clockwise and anti-clockwise. Yes, and geometric meaning is still the same. And just for free, you obtain that your map now satisfies the tetrahedron condition, but there is one problem. In the Veblen map, we have the free gauge function. Yes, and the gauge functions of the maps which enter the Zamolodchikov condition should be also adjusted. But this is not so complicated. But it is more complicated than this relation. I will go to it in the quantum case. Okay. And now we have formulas for the map. Let me discuss the the local Young-Baxter relations in this case. Let us consider the following map L, but now of two parameters, X and Y. Yes, and we have their 3x3 extensions, and their geometric meaning is as follows. Psi are just the homogeneous coordinates which enter the geometric picture. So, and the geometric meaning is that if you have a linear problem relating psi, psi1, psi2, and psi1, 2, so basically you remember that you had, just a moment, so these are the linear problems, yes? So the first linear equation was, is for psi, psi1, and psi2, yes? And here you have also psi, psi1, they give you psi2, and psi1, 2 is just not touched. Yes. So this is the meaning of that extension. So the important geometric part is the relation between psi, psi1, and psi2, which is just the simple linear problem. But now you can have a sequence of transformations described by the linear problem. So you had three linear problems here on the left, which allow you to transform psi, psi1, and psi2, psi1, 2, starting from psi, psi1, and psi1, 2, they allow you to go to psi2, psi2, 3, psi3. So psi, psi3, psi2, 3. And also the second part allows you to go from psi, psi1, and psi1, 2, first to psi1, 3, sorry, oops, to psi1, 3, this one, and also to end up with the same three vectors. And this gives you the Lax-Spar representation of the local Young-Baxter equation. Yes. And this gives you the formulas. And now there are 5 equations for 6 unknowns. And we have also 1 parameter free. And this gives you also these equations. And moreover, if you insert the restriction, which is motivated geometrically, so the affine reduction that y1, yi is related to x in this way. Yes. Then this condition fixes the gauge parameter. And this gauge condition is preserved. And then you go, I will show you. So I do not have that slide, but this gives you the local Young-Baxter representation of that Zamolodchikov map in affine coordinates. Just put y equal 1 minus x, and you will obtain another local Young-Baxter relation for that affine version of the tetrahedron map. Okay. And now what happens if you consider the gauge and the quantum reduction. So in that case, you know that your normalization map preserves the Poisson brackets, and the Veblen map preserves the Poisson brackets too, provided that the gauge function lambda has the special form with parameters alpha and beta. So, such a map preserves not only the Poisson brackets, but also the Weil commutation relations. So here's the corresponding result, and the relation between parameters alpha and beta of the maps. So basically, these relations give you that half of the parameters is free, and the second half of the parameters should be calculated from the relations. And so what I would somehow in our paper with Sergei Sergeyev, we showed that such maps, normalization and Veblen maps, can be realized by unitary operators, and their definition involves the so-called non-compact quantum dilogaret function by Faddeev. Okay, so basically this is all I wanted to present. And just as a conclusion, we have that as Young-Baxter equation corresponds to multidimensional consistency of two-dimensional systems, then the Zamolodchikov equation corresponds to multidimensional consistency of three-dimensional systems. And in this, the case of the Hirota map, the map could be decomposed into two pentagonal maps and a permutation. It turns out that the pentagonal condition is related to the symmetry of the Zark configuration. Maybe I will recall you. And if you take the symmetry of the Zark configuration seriously, then it will turn out that the Hirota map should be considered not as a map from n-dimensional integer lattice, but as a map from n-dimensional root lattice of type A. Okay, but it was a subject of another work. Okay, so I think I can conclude my talk, and maybe you would like to ask some questions.
Thank you. Thank you. Thank you very much.
May I ask a question? Look, you say that this Young-Baxter map is a kind of two-dimensional discrete equations and Zamolodchikov three-dimensional discrete equations. But there are also people talking about simplexual higher dimensional simplex, because it's, you know.
Yes, of course.
So is it any way to extend your picture to that? Because I struggle to find even more multi-dimensional integrable systems.
You see, I know some recent papers of Korepanov. I mean, he considered some solutions of higher simplex equations, and he was able to decompose those higher simplex equations into higher, higher dimensional analogs of the pentagonal equations. But I don't know how one can put into this projective geometry picture. Yes, but my problem is that so the Zark condition, which was important in the Hirota map, and it is also it also gives you the Zark maps, which are also three-dimensionally consistent. So this Zark condition holds in projective spaces over division ring, and it corresponds basically, it is responsible for associativity of the ring. And if you would like to go further, so somehow I would need a kind of relaxing the Zark theorem. And a possible way would be to go to some non-associative algebras, like octonions. But in this case, you do not have projective spaces. The only possible kind of projective geometry is for projective planes. And then somehow we would need to restrict ourselves. And for me, it was nice to have arbitrary number of dimensions of the space. In this case, where we relax the Zark theorem not to hold, it somehow it doesn't give me multidimensional projective spaces. Only projective planes are allowed. So somehow it is strange, because we know that some more dimensional integrability holds somehow. We have dispersionless integrable equations in many dimensions, and also in the papers of Korepanov, we have some more dimensional integrability. But I don't know how to insert it into this geometric picture. Maybe instead of having lines, or points of the projective space, we need to go to Grassmannians. But also in the Grassmannian case, all the geometry of the Grassmannians can be somehow we have also Grassmannians in the projective space, yes, where the Zark theorem holds. So the answer is that I do not know how to generalize the geometric picture I have to more dimensions. The only way I can see is to relax associativity of algebras. But then we restrict ourselves to projective
You
planes.
cannot go far relaxing non-associativity.
Yes, I mean, but there is also called for octonionic
That's it.
projective planes. There is a kind of weaker analog of associativity. But yes, non-associativity is strange. Yes. But you see, somehow, all the exceptional Lie algebras and Lie algebras are related to these non-associative projective planes. So, but I don't know how to generalize to more dimensions.
Adam, thank you very much. It was very interesting. I hope we can return to this question later, certainly in private communication, but for the moment it is very good, very interesting.
Okay, thank you.
Thank you. Thank you.
Thank you, Adam. Thank you.
Thank you very much.
much.
Thank you. Bye.
Bye.